So in this lecture we will study the earthquake response of inelastic single degree of freedom systems, and we will also be introducing the concept of inelastic response spectrum and design spectrum. So the first topic will be the concept of elastic design spectrum. By design I mean the design of structures for future earthquakes. We have already understood how we can construct the response spectrum of a past recorded earthquake. So we can run that past recorded earthquakes for different time periods, different single degree of freedom systems having different time periods for a constant damping ratio, and plot the peak responses against that past recorded earthquake to construct its response spectrum. Now the concept of elastic design spectrum will be different from the response spectrum of a past recorded earthquake. The design spectrum is intended for the design of new structures or for the seismic safety evaluation or performance evaluation of existing structures to resist future earthquakes, not the past recorded earthquakes, but for future earthquakes. The design of structures will be for future earthquakes. So for this purpose, the response spectrum of a ground motion recorded during a past earthquake is not appropriate. For example, you can see here that here you have the response spectra of different earthquakes which are past recorded earthquakes. The north-south component of the ground motions recorded at Imperial Valley is El Centro during earthquakes of 1940, 56 and 1968. So these are three different past recorded earthquakes: 1940, 56 and 68. So you can see here that they are having peak spectral accelerations normalized by the peak ground acceleration. This is also one representation of the response spectrum, that you normalize the peak spectral acceleration A with the peak ground acceleration. So 1 means same as the PGA value, and 2 means 2 times the PGA value, and similarly you can interpret all other points. So you can compare them. They are having peak values at different time periods. For example, this 1956 one is having a peak value at this time period around 0.5 second, but the other ones are having different you can say shapes or different variations. So this jagged response spectrums, irregular response spectrum, each one of them is characteristic of one particular ground motion excitation. Similarly, you can say that for each past earthquake, the actual response spectrum will be jagged curve like this, and they will not be having the peak response acceleration at the same time periods. So they will be exciting different single degree of freedom systems differently. For one single degree of freedom system, one earthquake will be causing the peak spectral acceleration, and now you have a new meaning of that you can simply multiply mass with the peak spectral acceleration to calculate the effective earthquake forces. So in other words, one earthquake will be causing the peak effective earthquake forces in one particular time period, but the other earthquake will be causing the peak forces in a single degree of freedom system having a different time period. So the peaks will not be necessarily at the same time period. So it is not also possible to predict the actual jagged response spectrum for the future earthquake. There is no known procedure which will directly give us the actual response spectrum caused by the future earthquake in all of its details for any ground motion which may occur in future. So it means that the design response spectrum for future earthquake should consist of some set of smooth curves or series of straight lines, and for each particular damping ratio, the curve should represent approximately the effective earthquake forces caused by the future ground motion. So it is not possible to predict a future ground motion or its spectra. So what we can do, we can just normalize or come up with an approximate smooth response spectrum, and that smooth response spectrum is called the elastic design spectrum. So different building codes develop those response spectrum, and those are recommended as design spectra for the design of different structures against future earthquakes. So we don't use the actual response spectrum of the past earthquakes, we use those approximate smooth response spectrum, and those are used as the design spectrum. So there are different procedures to construct such smooth design spectrum from the ground motion parameters which are expected at a particular site. So obviously, if you have a smooth response spectrum, the design spectrum of the acceleration versus time, which look like this, for example, the level of the spectral acceleration at each time period will represent the level of seismic activity or hazard level at that particular site. If you have two sites, one have the response spectrum which look like this, number 1, and the other have a response spectrum which look like this, number 2, you can say that the hazard level of the site number 2 is more than hazard level of site number 1. So the design spectrum should be representative of the ground motions recorded at the site during past earthquakes, with an assumption that the same kind of ground motions will be occurring again in the future also. So whatever type of ground motions a site has experienced in past, the same spectrum, the same representative of ground motions, the design spectrum should represent. If none have been recorded at a particular site, the design spectrum of that particular site should be based on ground motions recorded at other sites under similar conditions. And those similar conditions should basically include the magnitude range of an earthquake. If, for example, you have a site which is experienced in past by magnitude range of earthquakes 7 to 7.5, then you should use the same range to basically get a set of ground motions from the same kind of earthquakes to construct the design response spectrum for your site. The distance of the site from the causative fault, if your site is close to a fault, a seismic source, and that distance should be similar to the other ground motions which you pick from some other similar conditions to represent the hazard of your site. The other things which you should try to match while selecting the ground motions to construct the design response spectrum is the faulting mechanism, the geology of the travel path of seismic waves from source to the site, and the local site conditions at your site. So all of these parameters should be similar for those ground motions which you just select from any database so that they represent a future ground shaking at your site also. The design spectrum is based on the statistical analysis of the response spectra for the available ensemble or set of recorded ground motions. So what you can do is that you can pick different representative ground motions which represent the characteristics at your site, and those representative ground motions can be subjected to a statistical analysis. Their response spectra, actual recorded ground motions response spectra can be plotted, and then it can have a statistical analysis to come up with a smooth design response spectrum, and that represents the future earthquake or the hazard level of the future earthquake. So there are different ways to construct the design spectrum from the actual response spectra of past recorded earthquakes. We will not go into detail of such methods, but I will directly show you how the design response spectrum or the design spectrum looks like. For different values of damping ratios, this is an example response spectrum, example design spectrum for different hazard parameters which are selected. So this is an example for different damping ratios. For 5%, for 2%, 10%, 20%, and all of them have similar characteristics. They are not jagged response spectra just like the actual earthquake response spectrum. They are smooth response spectrum, and they have three distinct parts. One part in which the acceleration is increasing linearly, then it attains a peak value, and then it reduces with a nonlinear variation. So it is much smoother than the actual response spectrum of an individual ground motion. The individual ground motions may look very jagged kind of response spectrum, but this smooth one will be used for the design of new buildings or the performance assessment of existing buildings under future earthquake. So the design spectrum will be different from the actual response spectrum which is recorded for the past earthquakes and then converted into response spectrum. This is another elastic design spectrum, but now it is displacement versus time period. So for different damping ratios you can have these spectrum, and these spectra are different for different damping ratios. Obviously, as the damping is increasing, the spectrum is shifting towards downward side, so which means that the peak displacements are reducing. So these kind of smooth spectra, which are often prescribed by different building codes, they are used for the purpose of design of new buildings. So just like in the last lecture we calculated the peak response of one single degree of freedom system against El Centro earthquake, and that El Centro earthquake the response spectra, the DVA response spectra was given. So we just use the time period of the system to pick the peak displacement velocity and acceleration and convert it into FSO, the effective earthquake static forces, and those forces are applied to the structure to calculate other peak responses. For new buildings, for the design of new buildings subjected to any future earthquake, we will not be using that past recorded earthquake spectra. We will be using a smooth design spectrum which may look like this one or the one which was shown in the last slide, these ones. For your own damping ratio, you will pick the curve and then use it for the design purpose. Apart from this method, that you just select the representative ground motions from a set of detailed database of ground motions, and you apply a statistical analysis to the spectra of those ground motions to come up with the design smooth spectrum. There are some other modern methods of constructing the design spectrum also, and those modern methods include the use of probabilistic seismic hazard assessment or analysis, which basically considers the past rate of seismicity activity on all faults that may contribute towards the hazard of a particular site. So if you have a particular site here and if you have different faults around it, what this method does is that it considers the activity rates, seismic activity rates for each of the faults A, B, C, D, which may contribute the hazard at that particular site. And at the end of this analysis, you are going to construct the design response spectrum which may represent the future ground shaking, which will be a cumulative result of all of these the seismic sources A, B, C, D which are considered in this analysis. So there are certain modern ways of developing the design response spectrum also, but we will not be going into detail of this method or any other method of constructing the design spectra. We will be just introducing this concept for the purpose of design of new buildings or performance assessment of existing buildings. So this elastic design spectrum provides a basis for calculating the design force, basically the effective earthquake force for future earthquake, which should be applied in order to design the elements of a structure, and the deformation of single degree of freedom system U naught to be designed to remain elastic. Obviously, if we design our structure on this force, which is calculated from either K U naught or m times the pseudo acceleration, if we design our structures by applying this force, our structure is going to remain elastic during the design earthquake level. For this purpose, the design spectrum is used in the same way as the typical response spectrum for an actual earthquake, past earthquake. So just like we use that response spectrum for past earthquake, that we use the time period of our structure to pick U naught, or we use the time period to pick A, or spectral acceleration, and then these two quantities can be converted into the design forces, or effective forces or peak forces experienced during the earthquake. So we can use in similar manner the design spectrum also. So instead of that jagged spectrum, now we will be using a smooth spectrum which will be representing the future earthquake now. So the use is same. If we compare the design response spectrum with the actual response spectrum of a ground motion of an earthquake, there will be differences. Obviously, the smooth design response spectrum will also have that DVA form, the same form, the velocity, acceleration, and the deformation, the same kind of graph. So the graph will be, for design spectrum, the graph will be smooth, but for an actual ground motion, the graph will be jagged, just like this dotted line. So the dotted line for a real earthquake will always be different from the smooth response spectrum used for the purpose of design. And that difference is basically because the design curve, or the solid black line, is not representing one particular ground motion. It is not developed to match with one particular ground motion. In fact, it is constructed to represent the average characteristics of many ground motions. All those ground motions which are expected at your particular site. So all of those ground motions, they are all represented by this solid black line. So also there the differences is also due to the inherent variability in ground motions and responses. So each individual ground motion will have a spectrum which will not match with the standard design spectrum, but this standard spectrum will represent an average effect of the future earthquake loading, and then that can be used for the design of new buildings. So the design spectrum is different, conceptually different from the actual response spectrum of the past recorded earthquake, and that difference, it is different in two ways. One is that the jagged response spectrum is the plot of the peak response of all possible single degree of freedom systems, and hence it is the description of one particular ground motion. So this is very important. The actual response spectrum is just representing one ground motion, but the smooth design spectrum is a specification of the level of seismic design force or deformation as a function of the natural time period or damping ratio. So that the smooth spectrum is basically telling you the level of the seismic hazard at your site. The height of that spectrum is telling you that what level of seismic hazard you can expect in future at this particular site. So the actual earthquake will be different, it will be jagged, and it is only representing one ground motion. But the smooth one is representing a kind of a average effect of many ground motions which can occur in future, and it is basically telling you the level of seismicity, the level of seismic hazard, or the level of seismic forces which you may experience, your structure may experience during the future earthquake. And second is the difference is that for some sites a design spectrum is the envelope of two different elastic design spectra. So sometimes what you can do is that you can plot the actual response spectra of different ground motions and use their envelope as the design spectrum. So if you have one actual ground shaking in past which has this spectrum, and another one which may have this spectrum, another one which may have this one, so what you can do is that you can construct an envelope curve, and that smooth envelope can be used for the design of new buildings against future earthquakes. So this is also one difference between the actual response spectrum of the past recorded earthquake and the design spectrum for future earthquake. So here you see an example of a site in Southern California, and the site can be affected by two different kinds of earthquakes. One is having a low magnitude, relatively low magnitude, but that is originating on a nearby fault, and another one is having a very high magnitude, 8.5, but that high magnitude is caused by a seismic source which is San Andreas fault, and that is located at a very far off distance from the site. So you can see here that let's say there is a one seismic source, this is your site, and you have one seismic source A and another seismic source is B. That B1, this B is very far from the actual site, but it can produce a magnitude 8 earthquake or 8.5 earthquake. And let's say that the close source can produce a magnitude 6.5. So let's say that the seismicity at this particular site is governed by these two seismic sources A and B. So if you plot the response spectrum for the moderate sized earthquake, which is let's say 6.5 at a small distance from site, you can plot that spectrum, and then you can also plot the spectrum for this particular case where you have this distance from the source, very large distance, but the magnitude is also high. The shape of the second spectrum will be different. So one will be for moderate size at small distance from site, and the other one will be large earthquake at large distance from the site. The original shapes for both of the seismic sources is different, but since both are contributing to the seismic hazard at this particular site, so you can construct their envelope here. So the envelope will be like this, that this one, and then from here it will move like this, and then this one. So this envelope curve can be used as the design spectra for earthquakes at this particular site. This envelope will be for both of the cases. So the design spectrum for this site is defined as the envelope of the design spectra for the two different types of earthquakes which can occur at the, or which can contribute to the hazard of this site. The short period portion of the design spectrum is governed by the nearby earthquake. So in the short period range, basically this nearby earthquake spectrum was higher, but for long period the distant large magnitude earthquake was higher than that. So you use the envelope of both of them to be used as the design spectrum at that particular site. So this is a general trend. Also you will see in later lectures also that generally the small distance earthquakes which occur at the sites, at the seismic sources closer to the sites, those generally produce a high spectral acceleration at low short period structures. But for distant large magnitude earthquakes, they produce a high spectral acceleration at very large time period durations compared to the short ones. So here in the first range, low rise buildings, the seismic source A is governing the design. For this range, high rise building or medium rise buildings, the seismic source B is governing the design because it is producing a higher spectral acceleration compared to the first one. So this observation is very important. So now you can see here different response spectra, acceleration response spectra for different sites taken from different references, and they depend on not only the distance from the seismic source to the site, not only the magnitude level or seismicity rate of that particular seismic source, but also it depends on the site class, because different site soils or different site classes will amplify or de-amplify the ground motions differently. So the spectrum will represent or manifest that amplification thing. So you can see here that the typical rocks have a response spectrum which look like this solid blue line, where the peak spectral acceleration in the very short period range is high and the for large period range the peak spectral acceleration is low. On the other hand, you have the very soft to medium clay, this dark red line, and you can see here that its peak spectral acceleration lies in the moderate period range and high period range and not in the short period range. So different types of you can say site classes or soil types, they affect also the design spectrum. Another example for different soil types, the response spectrum, the design spectrum recommended by different building codes and different guidelines will be different, but they will be having a similar trend that for softer soils the peak spectral acceleration will be in this range around 1 second or 1.5 second. The high magnitude, high time period range, you can say relatively higher time periods. But for stiffer soils which are more towards rock sites, they will be having the peak values only in the very short period range. Similarly, another example you can see here for different kinds of soil types, S1, S2, S3 and S4 from this particular reference. This is the design spectrum, smooth spectrum, and you can now guess that S4 would be basically the soft soil and S1 will be the rock soil or very stiff soil. So another example from a relatively modern building code, UBC 97, you can say that you can see that this smooth spectrum have three parts. One is the linear acceleration increase up to a constant peak value, and then it decreases with a non-linear trend, and the curve is a function of two factors, CA, this CA and CV, and these two values CA and CV are the hazard parameters for your particular site. So the building codes prescribe the values of CA and CV for all sites, and you can use these numbers for your particular site to construct the design spectrum for your site. So here this way you can come up with the response spectrum for future earthquake by just following these building codes. So the methods to construct this design spectrum, they will not be covered in this lecture, and that will also be a very important topic. We will cover that in some other lecture. So this will lead us to the next topic, and that is the concept of inelastic response spectrum. I think I will end here, and I will cover this topic in next class. The general trend is like this, that building codes give you some particular numbers which are ground motion parameters. Ground motion parameters are the numbers representing the seismicity level or hazard level of your site. So these CVA and CV are the ground motion parameters or seismicity parameters. Every building code gives you these numbers, and those numbers can be picked from the code based on the site class, based on the seismic zone and all other factors. Those are representing the site at which you are going to perform this analysis. So the general equation or the shape of response spectrum or the design spectrum is the function of those ground motion parameters. So different building codes give you these parameters for your site. You follow that code, pick those parameters for your site, and using those parameters you construct the design spectrum for your site. Then this spectrum start representing the future earthquake which can be expected at your site. So for case of UBC 97, those parameters, the site parameters are CA and CV, and the procedure to pick CA and CV value for your particular site can be found in UBC 97. So you need to have an information about the site class of your site, the soil type basically, site class, and second thing is the seismic zone. UBC 97 propose a seismic zoning of a particular area. So if you know that which seismic zone your site is in, and what site class is it represents. These two informations can be used to pick CA and CV for your particular site, and then it can be used to construct the response spectrum, design response spectrum for future earthquake.